Hi everyone, I'm Kotsin, and I'll be giving an overview of our work, InfoMax-GAN. There is a QR code on the top right-hand corner, which you can scan to be directed to our paper. While GANs are useful for numerous applications, they suffer from certain problems. In this paper, we focus on mitigating two of them. Firstly, the mode collapse of the generator, which results in generator images of very poor diversity. Secondly, the catastrophic forgetting of the discriminator, which contributes to an overall unstable GAN training environment. In our work, we aim to mitigate mode collapse via contrastive learning and catastrophic forgetting by using information maximization to improve discriminator representation learning. Our main insight is that both approaches can be combined into one based on the deep InfoMax work introduced in ICLR 2019. Doing so, we show our approach has a very wide range of improvements. In the interest of time, I will only explain the first three advantages, with the remaining details available in our paper. As usual, the discriminator sees both real and fake images from the dataset and the generator respectively. The images are passed through the initial layers of the discriminator CSI1 to CSI-N to produce the local feature map CSI-X. CSI-X is then further encoded into the global feature vector ESI-X that is finally used in the GAN objective task. Next, we pass the local and global features to critic networks phi theta and phi omega, which are simple MLP networks with spectral normalized weights. These networks project the local and global features to a higher dimensional space that using a dot product between feature vectors can capture the similarities. The projected features then undergo contrastive pairing, where a positive sample is given by pairing an image's global feature vector with one spatial vector from its own local feature map. Negative samples are then given by pairing the same global feature vector with either a spatial vector from another position in the image's local feature map or a spatial vector from a different image in the same mini-batch. The positive and negative samples are then used to compute a simple softmax classification loss. For details, please refer to our paper. To show that we mitigate mode collapse, we demonstrate that when a generator has less mode collapse, the more diverse the generator images are, which leads to easier negative samples in the contrastive task, and thereby a higher accuracy. To do so, we simulated generators with varying degrees of mode collapse by restricting the diversity of images with CIFAR-10 test data. Our experiment shows that, as expected, the more mode collapse the generator is, the worse the contrastive task accuracy, reaching almost zero in the case of total mode collapse. To show that we mitigate forgetting, we follow a similar setup as in SS-GAN, where we show that a discriminator classifier in the sequential 1 versus all CIFAR-10 classification task would experience forgetting when the underlying class distributions changed. However, when regularizing training with our objective, the classifier can easily prevent this kind of forgetting. We compare our results to two models, the baseline SN-GAN and the state-of-the-art SS-GAN. For fairness and comparisons, we re-implement all models, use the same architecture and the exact same training and evaluation conditions with no hyperparameter tuning for our method. Overall, for all three metrics of FID, KID, and inception score, InfoMax-GAN is able to significantly outperform the baseline SN-GAN. Compared to SS-GAN, we further improve our performance on the challenging high-resolution ImageNet dataset by a significant margin of around 3.6 FID points. Importantly, while SS-GAN fails to improve over the baselines for image domains like faces, our method is able to significantly improve over both SN-GAN and SS-GAN for all metrics, suggesting that our approach is versatile across multiple image domains. Our method also greatly stabilizes GAN training across a wide range of popular training settings and significantly improves FID compared to the baselines in all these settings. In practice, the number of discriminator steps, MDs, is a significant bottleneck in training time. It shows that even at low values of MDs where SN-GAN training cannot converge, our approach can allow for convergence and significantly improves FID. This suggests our approach can be useful for situations where one is training GANs with a fixed computational budget or on new datasets where the optimal training hyperparameters are not known in advance. Finally, when profiling the time taken for 100 generator updates, we show our approach has very low computational cost compared to the main bottleneck in training time. In summary, our approach addresses problems at both discriminator and generator, and through doing so, we demonstrate a wide range of benefits compared to the state-of-the-art works. We hope our method could become a practical approach for future work involving GANs, especially for researchers and practitioners planning to use GANs for novel applications and datasets. For more details, please refer to our paper. Thank you.